everyone. We're going to use the principle of mathematical induction to prove that this sequence, arithmetic sequence, equals this sum over here. I don't know why that's moving, but okay. So basically, this is for all positive integers. So we're only talking about positive integers. So the first thing we're going to do, and there's 3 steps basically. You want to show, assume, and prove. So the first thing is to show. And the show part is to show that it's true for n equals 1. So we're going to plug in 1. You can plug it in each of these pieces, and you get 1 equals 1 times 1 plus 1 divided by 2. And that's going to give you 2 divided by 2 here, which equals 1. So they all match. And it should equal your first term, because this is your first term. Now again, like I did in other videos, I want to show for what happens when n equals 2. When n equals 2, it should be the sum of the first 2 numbers. So when I plug in 2 in here, I should get the sum of those, which is 3. So let's plug in 2. So you get 2 times 2 plus 1 divided by 2. That equals 3. And if I did n equals 3, I should get the sum of these 3 numbers. And these 3 numbers, so this would be plus a sub 3. So the sum of those numbers would equal 6. So let's plug in 3. And this is 4. 4 divided by 2 is 2, and 2 times 3 is 6. So that's basically what you're doing. This is your sum right here. So now, let me get rid of this, because you don't have to do that. All you have to do is show for n equals 1. So we did the show part. Now the assume part means you're going to assume it works for n equals for some k. So what you do is you just write down this same problem and everywhere there's an n, just put k instead. Alright, so all we did is copy this down and put k. So we did the assume part. The prove part means we want to prove that it works for n equals k plus 1, which means the next number, just like we did here. Did it work for n equal 2? Did it work for n equal 3? Does it work for n equal 4? And so forth. So for any next number, k plus 1. So what you do is you copy this part down. 1 plus 2 plus 3 plus dot 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 plus k. Now the next number is your k plus 1. So you just put k plus 1. So that would be your next number. All right, if this was 5, then the next number would be 5 plus 1, which is 6. So that's what that means. Now on this side, you've got to also add the next number to this sum. So everywhere there's a k, you're going to put k plus 1. So this k, you can put, k plus 1. And this one's k plus 1, so the next one is k plus 2. And then you have this divided by 2. Now again, if you didn't get what I said with this k plus 2, what you're really doing is you're taking this k and then plus 1. Instead of writing k, you write k plus 1. So there's where you get your 2. Now we have to prove that the right-hand side looks like the left-hand side. And what's nice is we already know what this part equals. This part equals this. So let's write that out. So that's k times k plus 1 divided by 2. And our next term we have to add is plus k plus 1. All right, and this is supposed to equal this whole thing here. To save room, I'm going to not write that down. So to get a common denominator, what we want to do is have a 2 under here as well. So I'm going to put, if I put a 2 here, I have to put 1 here. Now let's simplify this. You get k squared plus k, I'm just foiling this, plus, let's foil this, 2k plus 2. And this is all divided by 2. So we already have our 2's matching. So all we have to do is get our numerators to match. So let's add all this up. We get k squared plus this 2 is 3k plus 2 divided by 2. Now I want it to look like this side, so I got to factor this, and this is going to be k plus 1 times k plus 2 divided by 2. And they match, so we did our proof right here. And that's it. Thank you. Have a nice day. Bye-bye.